Okay, so we are at the home stretch. We have tomorrow will be the last day of lecture officially. Last day you have to be online for lecture. There will be no more lectures after that. So we have a final. You have your exam that's going to be due tomorrow officially. I mean, unofficially. Officially it's due tonight. So that's exam 3. Thank you. And then you have your final that'll be left. That's it. Okay. So are you guys ready? Ready to be done? How's your presentations going? Yeah, everybody's putting in an effort. You came on Friday at 8 in the morning. You didn't even eat. That don't mean anything. I come on Friday at 8 in the morning every day. So, well, not Friday every day, but every Friday. Okay, so we want to finish out strong. We want to make sure that we get our degree, that we earn our degree, right? Okay, so Avenel, you guys have 2 labs to do today, right? Fireball, you have 1 lab left to do. That will be your last labs, okay? So we'll be doing that later on today. Today, we're going to be going over chapters 9 and chapters 10, and if we're lucky, chapter 16. If not, we'll be finishing chapter 16 tomorrow, and we'll be doing a little bit of 4 and 14, okay? Okay, are there any questions about anything? I like it when there's no questions. No, unofficially, yes. Officially, everything is due on Friday, yes, because your class ends on Friday, okay? Yeah, tomorrow, yeah. 11, well, you should have it online on your page by 11:59 p.m. because that's when I'm grading it, but in theory, you should have it done before that because by the end of that day. Yeah. Yeah. Yes. Of the ones that we're doing today? You got that one opportunity. I'm not rich. I can't be spending all the money on paper. I killed thousands of trees already. Yeah. Okay, repeat that one more time. That's right. I should get 1 copy only, right? And so, and again, really, it should all be on your page. I should be able to find it all on your page, right? So I should be able to go to your page and get it there. You can also upload it. That's fine. But if you have it on your page, don't worry about uploading it because it's there on your page, okay? The other thing is that because, you know, we're in crunch time. I am going to there are going to be 2 things of extra credit that are going to be available. One of those is that the top 3 parities will get so many points based upon your guys' vote, right? Who you guys vote for in terms of parities. So you guys need to get your parities to Israel so Israel could actually put them in a compilation so you guys can actually go through and vote on it, okay? And so based upon that, you guys, top 3 will get a extra credit added onto their exams. So, and I know that some of you guys need a little extra credit. I know some of you guys are perfect and, you know, have that 99.99, right? But some of you guys are, you know, kind of paddling there, right? So you may want to definitely get that parity to Israel as soon as possible so that we can get those up. If you don't submit one, then, you know, hey, you didn't want the extra credit. That's the way I take it. Okay. Anything else that I need? Okay. Okay, so let's get started, all right? So we talked about what happens when we put salts into water, right? Into an aqueous solution. It separates. We form these nice little ions. Okay, there we go. Okay, so in the case of potassium sulfate, what would be the dissolving equation? So what would happen in the case of potassium sulfate if we added it to water? Okay, help me. And how would I write that chemically? So we have our potassium sulfate. Remember, reactant. So we're going to put in water. And what's going to happen? What are going to be the products? Did you say K2? So I have K plus SO, SO4, SO4, is there anything else I'm forgetting? 2 and 2 in front of the K or 2 on the K? Subscript or coefficient? Ah, so you say coefficient. Okay. Anything else? The letter? What letter? SO? AQ? A for aqueous, Q. All right. That's a Q, it's not a G. Q. Okay, anything else? Now, tell me, potassium sulfate, what type of compound is it? Jordy? What type of compound is it? Well, we know it's a solid because it has S next to it. But what type of compound? Is it covalent? Is it ionic? Is it metallic? Who's somebody? I heard ionic. So it's an ionic compound. Okay. We know that if it's an ionic compound, it should have what when it dissociates? What causes an ion to come together? Well, metal and non-metal, that's one thing. But what specifically about that metal and non-metal that causes them to attract to each other? Oh, charges. Charges. Are we missing anything then? The charges. So what would be the charges? Is it just one negative? Okay, so we want to make sure that we incorporate those charges. We can't forget that. That's part of being ionic. We know that ionic compounds will dissociate when they're put in water. Not all of them, a lot of them do. Okay. Now, what about calcium nitrate? So if I have calcium nitrate, although it doesn't say write the dissociation equation, we're going to write the dissociation equation. We're going to be a rebel. Calcium nitrate. So what's going to happen when we put that in water? It's going to dissolve into what? Into an aqueous solution, okay? Made up of what? Ions, okay, so what ions am I going to have specifically? Tell me. Okay, now tell me which anion and which cation will I have? Okay, so calcium, what's going to be the charge on calcium? I heard somebody say +2. And I'm going to put that aqueous. And then the nitrate. There should be 2 of them, that's right. And it's important that you guys realize, so what's holding them together? The reason why you have two of them here is because you have that calcium, right? So if you don't have that calcium there, it causes them to break up. They're not going to be held together, okay? So each of those nitrates are going to be independent. So that's why we have two of them as a coefficient rather than as a subscript. Do you guys get that? You guys know Velcro, right? How many of you guys have Velcro shoes or had Velcro shoes at some point? The little straps. Yeah, you have, yeah, exactly. See, he has Velcro shoes, exactly, right? So what happens when you take that strap apart? And it loosens it up. Isn't that guy just flapping around unless it touched something else, right? So it's kind of like Velcro. You have a positive charge and a negative charge. It's like your two Velcro strips. What's holding it together is the Velcro, right? The Velcro allows it to sit there and stick. If you don't have that one Velcro, then it's not going to stick. That other half isn't going to stick. Does that make sense? Okay. Let's see. Okay, so somebody has a question. Good job. Response. Okay, so acids are just a special case of ion, right? What makes an acid again? The hydrogen in the aqueous. The fact that you have that hydrogen and we're putting it in the aqueous solution, that makes it an acid. It allows it to separate if it's a strong acid. Strong acids will completely dissociate. Weak acids won't. Yes, you're raising your hand. Okay, so what is the definition of a strong acid? No, you're right. It's able to give a proton. You're right. Yeah, it is a proton. H plus. H plus is just is a proton, right? Because it doesn't have any electrons and it doesn't have a neutron. So it only has a single proton. Okay. So an acid is able to give H plus. So a strong acid is something, what makes it strong? Just said it. What was that? The proton, which means that it has to do what? If the protons are available, it has to be able to do what? What was that? I just said it. It's good. I get to know how well they listen to me, you know? A strong acid completely dissolves or dissociates. Yes. So a strong acid is going to completely dissolve or dissociate. That means that you have a whole bunch of H pluses available, right? So if it doesn't dissociate, you're not going to have those H plus available. That's not going to be a strong acid. So a weak acid, well, we know weak acids will have carbon in it. That's true. What else? It would have less H plus to give out, meaning that they're not dissociating. They're staying together. Okay, so we have two acids up here. We have hydrochloric acid and we have nitric acid. Both of these acids are strong acids. As we represent it, we have hydrochloric going into water. It completely dissociates. It forms what we call the officially, this is what the hydronium ion looks like officially. But we will always substitute it as H plus because it's a lot easier to see that H plus. That H plus, it gets in contact with water. It holds on to water like, oh, I love water. They won't let it go, right? That's H plus. So then it forms H3 plus, which then goes to you and tries to rip off your face, right? Well, that's the only thing that you guys ever get. You got to get that extreme, you know? I know. Okay, so In the case of nitric acid, it does exactly the same thing. It dissociates completely, right? Battery acid, I think, is phosphoric, but I'm not 100% sure, or sulfuric, one of the two. So, but I don't think it's nitric. But it is a strong acid, okay? So, and it makes sense. It's a strong acid because it has those charges that we can actually use to sit there and help electrons go through it. Literally, you have this nice little battery that has those plus and minus charges that are sitting in there, and you're flowing electric current through it. They're able to conduct electricity because they're completely dissociated into their ionic compounds. That's right. Okay. So we also have certain acids like sulfuric acid that are polyprotic. Polyprotic basically means that it has more than one H plus to give. It can give two H pluses. Or phosphoric acid. How many phosphoric acid do you guys, what is the chemical formula of phosphoric acid? Anyone? Fireball. Let's see. Louis, chapter 9. Luis, are you there? Anybody from Fireball?
Would it be H3PO4?
H3PO4. That's right. H3PO4, how many H pluses can it give? It can give 3, right? So it's considered to be polyprotic. It'll get rid of that very first one, then it's able to get rid of the second one, then it's able to get rid of the third one. Similar to what you see here with the sulfuric. In the case of the very first one, it gets rid of the first H plus, and then it forms HSO4 minus hydrogen sulfate. Then hydrogen sulfate then is able to get rid of the second. And then it just forms that the hydronium ion and sulfate, okay? So it completely dissolves, okay? Now, in the case of, and if you pay attention, and if you guys have been looking, we have the arrow going in a single direction. The reason why we have the arrow going in a single direction is because it's a strong acid. That means that it's going to completely dissolve. That means that it's not going to be able to reform itself readily or easily, right? It's able just to completely dissolve. That's it. Okay. Are you guys with me? Okay, good. Now, acidic acid, which is vinegar, is a weak acid. Do you guys drink vinegar? Every morning you get up and take a spoon of apple vinegar to help your blood or help your body. Okay, or you use vinegar to cook, right? Sometimes you use vinegar to cook or to clean, yeah, right? So, and do you guys wear gloves when you work with vinegar? You do? I don't. I'll just start drinking out the bottle too, you know, like, you know, a little vinegar, right? Yes, you can. Okay, so in the case of vinegar, vinegar is a weak acid. It has carbon in it. Like Margarita told us, anything that has carbon in it is going to be a weak acid. So since it's a weak acid, that means that H plus isn't going to want to dissociate that often. So in this case, we make it so that this equation becomes an equilibrium equation. Do you guys know what equilibrium means? What does equilibrium mean? Equal means the same, right? Or basically what an equilibrium equation is, it means that the equation can go both directions, right? So it can go in the one direction and it can go in the other direction. It's not going to be exactly the same. This guy, the reactant side is favored, meaning that we're going to have more stuff stuck in the reactant side than in the product side. So then we're going to have a lot more that are going to be attached to the acetate. So that H plus is still going to be attached to that acetate. So it's not going to be able to get rid of that H plus, right? like you see over here. So it's going to favor this side more than the other. But the other side exists, but it's going to be at a very low level. So usually if we draw the arrows, although we didn't show it here, the arrows are drawn so that it favors the side that is the most abundant. Okay, so this arrow going in this direction would be bigger than the arrow going in the other direction because it's more abundant. So again, this is called an equilibrium equation. It basically means that both your product and your reactants still exist in that solution. Okay, do you guys kind of get what I'm saying there? Not all weak acids are organic compounds. That is the wrong statement. Not all weak acids are carbon acids. A lot of them are, but not all of them. I'll talk about one here in a minute. Okay. So when we talk about acids, we said a strong acid are the ones that are going to be able to completely dissolve in an aqueous solution, or almost completely dissolve in an aqueous solution. That's going to be a strong acid. So in the case of a strong acid, the major species is always going to be the ions separated, okay? The minor species, major meaning the most abundant, right, major. Minor species is going to be the one that is less abundant. So the less abundant species of the acid is the acid that's together, right? So in that case, if we had HCl as our acid, we know that HCl is a strong acid. So the major species is going to be that hydrogen ion and the chlorine ion. The minor species is going to be the HCl together. Does that make sense? I'll show you what I mean here in a second. Now, the weak acids are going to be just the opposites. Weak acids, they're going to be horrible at conducting electricity. They're going to be, they're going to ionize, but they're going to ionize just a little bit. So the major species is going to be the unionized, basically the stuff that's still stuck together, right? And the minor species are going to be the ions, okay? So let me show you what I mean. It's what? It's not well dissolved. A weak acid is not well dissolved. That's right. So where a strong acid is well dissolved. Okay, so if we take a look here, the very first one is hydrochloric acid, HCl. So if you take a look in it, you have the Mickey Mouse ears, that's water, right? The red guy with the two white, so that's water. Chlorine, and you have sodium, right? I mean, sodium, hydrogen, a hydrogen ion surrounded. Okay, so here we have the chlorine ion surrounded. You have the hydronium ion surrounded, the hydronium ion, the chlorine ion, okay? So they're being surrounded by water, completely dissolved, okay? You don't see any of those together, okay? So that's a sign of a strong acid or a weak acid. That's a strong acid. Okay, so a weak acid, here, that's acetic acid. Here, this is acetic acid. Here, this is acetic acid. Here, this is acetic acid. Here is that hydronium ion. Here is the acetate ion. So we have one acetate ion and one hydronium ion, but all of the other species are all connected together. It's that acetic acid. So is that a strong acid or is that a weak acid? It's a weak acid because you're not getting complete dissociation. The most abundant stuff in there is still connected. You guys get that? Are we here? Okay. Okay, so Marguerite was dead on. She was like, okay, carbon acids are weak acids, carbon acids are weak acids. Are all carbon acids weak acids? Are all acids that are weak acids carbon acids? No. Hydrofluoric acid, even though it has that ick, hydrofluoric acid is a weak acid. Now, hydrofluoric acid is like a very special case of a weak acid because you would assume that it would be a strong acid because, you know, fluorine the way it is, you know, and it ends with ick, and I told you guys it ends ick, so you say, oh yeah, it has to be strong acid. Now, what makes it a weak acid is because it doesn't like to dissociate. Hydrogen, I talked to you guys about this before, it's a bully, right? I said, oh, he's a bully, right? Not hydrogen. Fluorine is a bully. Fluorine likes to be in control of the circumstances. He likes to decide when he breaks up with somebody. He likes to decide when you can leave and when you can't leave. So fluorine is like, nope, you cannot go. You stay right here. Have you ever met anybody like that were so clingy they won't let you? You can't go to the bathroom by yourself. They want to try to control what you do, right? Where are you going? Where are you going? You can't go anywhere. You didn't tell me you were going. You can't go anywhere. No. You've not met anybody like that? Oh, okay. So, yes. So, fluorine is like that. With hydrogen, it's like, no, you cannot go. You can't go until I want you to go, right? And he's not going to let hydrogen go unless he finds something better than hydrogen. It's like, no, you're my girl until I'm ready to dump you, right? You have no say in it, right? That's right. So that's what makes it a weak acid, because it's so strong that he won't let that hydronium ion separate. Where chlorine was like, hey, you do what you want to do, bye, you know? And so they separate real easily in water, where hydrofluoric acid won't separate. It makes it weak. So the abundant species in the case of hydrochloric acid is going to be what? The ions or HCl? The ions. So it's going to be the hydronium ion, the H plus, and the Cl minus. The minor species in the case of hydrochloric acid is going to be HCl. Okay. Now, what about hydrofluoric acid? What is going to be the major species? Major species. So here are your options. You have HF, H plus, F minus. So HF. So HF is going to be our major species, right? Because it's not going to want to dissociate. Weak acids don't dissociate, or they dissociate very little, okay? Okay, and so if you take a look at the equation, right? So we have hydrochloric acid and water, it completely dissociates, and so you favor the products, you favor the ions. In the case of hydrofluoric acid, you're favoring the hydrofluoric acid, so you're gonna have more of these guys than this, and so your arrow is gonna be bigger going the other way, right, towards the reactants. Are you with me? So what does that look like? Okay, strong acid, you get your ions. A weak acid, you get the compound together. Simple? Okay, these are 7 strong acid. You'll notice that they all end with ic. Nitric acid, sulfuric acid, hydrochloric acid, hydrobromic acid, hydroiodonic acid, chloric acid, perchloric acid. So all of those are examples of strong acids. Okay, so do all acids have hydrogen? Yes. So if it's an acid, it usually will have hydrogen. Now, there are things that will be described as being an acid, right, that don't have hydrogen. They're said to be acidic. Those are special cases. We'll talk about that when you guys get into Chem-1A, those who are deciding to go to Chem-1A. Oh, you know you love this class. You guys love it so much that you guys may want to take it again, right? That's what I was understanding, right? Okay, so you guys understand about weak acids, strong acids? Are you feeling comfortable? Okay. What was that? We will talk a little bit about bases, but not too much. But we will talk about nitrous. Nitrous acid, OUS, those acids, is that a strong acid or is that a weak acid? Okay, anything that ends with OUS means it's a weak acid, okay? So if it has that ick, that's kind of a hint that it's gonna be a strong acid. Which one? Hydrofluoric, because I told you that was an exception. You're always gonna get exceptions. Because I tell you it's an exception. Well, now you know, right? You read it in the book. Okay, so what is going to be the major species for nitrous acid? What does nitrous acid look like? What is the chemical formula for nitrous acid? Just NAQ? I heard somebody say NH? Nitrous acid. I hear somebody say it's N, and I hear there's an H. Is there anything else in there? An O. How many O's should I have? 2 O's. That's right. I should have 2 O's. AQ. Can I draw it out? Yeah, it's a piece of cake. Yeah. You guys should be, if you can't draw it out, you should be able to draw it out at this point. So it's H plus. Somebody has their hand up. Yes. And what does the nitrous, how many, let's say, first off, it's NO2. What is the charge on it? What would be the charge? It would be positive? Are you sure it's -3? NO, what should be the charge on, and this guy would be called what? This NO with that negative charge? Did you say nitrate or would it be nitrite? Yeah, it's all part of it, right? So if I was drawing the structure, because you asked me about the structure, this is nomenclature, right? So this is nitrous acid, right here. This is nitrous acid. The way it looks is you have N. How many electrons does N have around it? It has 5. Okay. This here means I have how many more added on? How many? 1. 1 additional 1. Okay. So, and then I have O's, right? He wanted the structure, right? Isn't that what he asked me? Okay, so in this case, this guy has his octet. What about this guy? The nitrogen? No, so we need to make some adjustments. Can you guys see my dots? That's right. So that's 2, 4, 6, 8. So what it means by that is you're giving up an electron, right? So in the case, you're giving up a single electron. The electron is now going to your negative ion, right? This guy becomes plus, right? And these guys are going to interact with each other based upon charge. This guy is a plus, this guy is a minus, and they're going to be able to interact solely on that charge. Where this guy is a polyatomic ion, right? It has a charge. The whole thing is charged. It has a negative charge associated with it. So that negative charge will interact with that positive charge. It's on the outside. No, this is ionic, right? This here would be polar inside here. So polar is only described to, it's only used to describe whether things are covalently bonded. These guys, meaning that they're sharing electrons. This guy gave up his electron to this guy. Do you understand? Okay. Okay, so what would be the major species in the case of nitrous acid? Would it be the ions, the H plus, the nitric ion, or would it be nitric acid? Nitric acid would be the major species. Because it's a weak acid, that means it stays together. What do you mean? Yeah, they're interacting together by charge. That's right. That's right. Okay. So in the case of chloric acid, what does chloric acid look like? Chloric acid. HCl ClO what? Are you sure? Yes, ma'am. Yes, you may. Is that chloric acid? Are you comfortable with that being chloric acid? O3, yes, because it would be the chlorate ion, right? What does chlorate look like? ClO3. That would I ate organic apples, despite them being poisonous. Come on, that was just the other day, right? Okay, so in the case of chloric acid, is this guy going to completely dissociate, or is it going to stay together? You think it's going to dissociate? It's going to separate. So we're going to have the H plus ion and the chlorate ion. Okay, so this is the major species because it's going to completely dissociate. Simple. Jordy, you look like you got a headache. Got it? Okay. You do got a headache? That's good. It means you're using your brains. Okay, Enrique. No Enrique. Okay, Juan. So Juan will take Enrique's spot. Jose. Okay, Jose. So now, up until this point, we have been doing conventional equations. So this is an example of a conventional equation, right? Where we write everything out, everything is stuck together. But we know what really happens. We know that ionic compounds will dissociate, won't they? So if it's in water, AQ, it dissociates. That means it dissociates. If it has an S, that means it stays as a solid, right? So are you guys with me? Okay, so since we know that things completely dissociate, I'm going to show you another way of writing your chemical equations. All right, yeah. So here, this is an example of a conventional equation. Okay, so we have lead 2 nitrate reacting with sodium chloride. And we know that it's a, what type of reaction is this? A double displacement reaction. Okay, so we got a double displacement reaction. We know that we're going to get a solid for one of them because they tell us. We're going to get lead chloride, lead 2 chloride, and we're going to get sodium nitrate. Okay, so let me show you how we would write this as an ionic, a total ionic equation. Okay, but you got to help me out. And Jose is going to help me out, and Juan is going to help me out. So, because it'll make it a little bit easier to understand, and it also help us to understand when things dissociate and when things stay together. Okay, so Jose, we have lead nitrate. What is lead nitrate going to dissociate into? Lead. Is it going to be just lead, or is it going to be some type of ion of lead? What ion of lead will we have? Lead what? Lead 1, lead 2, lead 3, lead 17. Lead 2, that's right. So that means if it's lead 2, that means what is the charge on that lead? Positive. It's positive ion, positive what? Positive 2, because it's lead 2, right? So it's lead 2, and we put AQ. And what is the charge on that nitrate? It's a negative. So NO3 negative. AQ. How many of these am I going to have? How many? I heard somebody say 2. That's right. So am I going to use that as the coefficient or as the subscript? As the coefficient, because it's like the Velcro, right? If you had 2 things that are attached to it, they're going to separate independently. So it's going to be like the coefficient, right? Okay. 1, sodium chloride. So what is that going to dissociate to? So Na for sodium. Okay, what is going to be the charge on sodium? Positive. The metal, man, come on. We know that metal is positive. Okay, and that isn't true. Metals are most of the time positive. Okay, okay, and chlorine, what is that going to be? Is chlorine? Okay, it's negative. Okay, so anything that is an aqueous, it says aqueous, it's able to be dissociated. So we're going to dissociate. Yes, ma'am. Man, you're so good. So I need to put a 2 in front of the Na. What about the Cl? That's right. And let me finish. Good job. So we need to put that coefficient in front of both of them since they are separated. You no longer have that Velcro holding them together, so you have 2 of each one. Are you guys with me? Can we see each other? Good. Okay. It is a double replacement, yes. because we're breaking them all down individually. Yeah, yes, it does. That's what really is happening in the solution. So yeah, in real life, what's happening is that everything is separated. As soon as it hits the water, it's separated. Okay, so that's what's really happening, right? We showed you the old way, the conventional way, because it's convenient. It's easy to see, right? But we're trying to show you what really happens now, right? We're building you up, you know? Yes. Yes, you do. It makes it fun though. It's like a really cool puzzle once you get it. No, I teach everything. Okay, so to an extent, yeah. Yeah, in a sense. But you still, like with anything, like if you say your ABCs enough, you'll mess up every once in a while, right? So anyway, let's move on. So the other thing that I wanted to say is things that are solid, that are liquid, or that are gas, they can't be separated. Okay, do you want me to repeat that? Things that are solid, that are liquid, and that are gas cannot be separated. You want to repeat it one more time? No, actually, you guys repeat it. So, okay, things that are solid, liquid, or gas cannot be separated. Okay? So, do you guys have that ingrained in your head? Say it one more time. Okay, so can I separate this? Why? Because it's a solid. So we just write it down as it is. Okay. So what about this sodium nitrate? Can that be separated? Yes, it can. Sorry, I'm running out of room, so I have to. Okay, so then what is it going to break down to? Nope. Aqueous means it's in water. Okay. Okay, so now you'll notice when you guys did math, when you had something on one side of the equation and one thing on the other side of the equation, could you get rid of it? So let's say if I had a 2 on this side of the equation and I have a 2 on this side of the equation, could I get rid of it? In math, you guys don't remember that? Let me see. Let me make sure that I understand what I'm saying. Let's say I had this equation here. I'm going to write an equation up here. So I have 2 on this side of the equation and I have 2 on this side of the equation. Can I get rid of it? Because literally, if I bring it to the other side, it'll disappear, right? Yeah. So then I get x is equal to 0, right? Okay. So, but that's true. I could do that. So if I have things that are on both sides of the equation, I can get rid of it. Okay. I just want to be sure. Now, the same thing is the case in chemistry, right? If you have something that is exactly the same on one side of the equation and exactly the same on the other side of the equation, I can get rid of it. These guys are called spectators, right? Have you guys ever went to a party? Okay, so have you guys ever went to a party and saw that guy that came to the party and just sat against the wall? Okay, so those guys would be an example of a spectator because they come to the party and they leave by themselves. They come to the party and they leave by themselves because they don't talk to anybody, right? Okay, So those are called spectators. So we're going to get rid of our spectators. So they're going to be the guys that are exactly the same on one side of the equation and on the exactly the same on the other side of the equation. Do we have any spectators for this chemical equation? I don't? Yes, I do. What do I have? Okay, I have 2Na and I have 2Na. Okay, and okay, 2NO3. Because they're exactly the same on both sides of the equation. That's why they will be spectators. Okay. So these guys are going to be canceled out. And this here is called our total ionic equation. And then what we call our net ionic equation, I'm going to write that up here, net ionic equation. We basically just get rid of our spectators. So then all we have is lead, 2 ion, plus 2 chlorine ion, yields lead 2 chloride. Solid. Okay. So that is our total ionic equation. Yes. The spectators. Yes. So we've gotten rid of our spectators. Okay. So spectators, again, you'll see them exactly the same on both sides of the equation. Those are your spectators. Okay. Are you with me? Okay. Okay. So this just basically tells you everything that we've talked about, that whole process. So let's see how well you guys can handle it. It says, when a strip of magnesium metal is placed into iron 3 chloride solution, a magnesium chloride solution results and solid iron forms. Develop the net ionic equation for the reaction. Okay, let's see. Diego, help me out here. It says when a solid strip of magnesium metal, okay, is placed in an iron 3 chloride solution. So is that my reactants or are those my products? Those are my reactants. Okay, so that means they're going to be on what side of the equation? Left side. Okay, so what does magnesium metal look like? What is the chemical formula? Mg. And it's a solid. Okay. Now what about iron 3 chloride? Fe for iron. Okay. I heard somebody say Cl3 aqueous, right? We know we need 3 chlorines. Why do we need 3 chlorines? Because of the iron charge is 3+. And you said it's aqueous, since it's a solution, AQ. Chemical equation. So balanced chemical equation is considered the conventional equation. Net ionic equation is when you break it up into ions and you only show the ion. The net ionic, yes, when you show just the charges ones, yes. The one that we just did. conventional, if it says conventional balance equation, but either case, you need to balance the chemical equation first. Now you always should find the conventional equation first. That's what we're doing first. Okay, so what are going to be the products? What are the products? Haley, what are going to be the products? Do we? Not yet. Just tell me what are going to be my products first. And then we can go about the charges. What am I going to make? It says a magnesium chloride solution results and solid iron forms. MgCl2, good job. Is that solid, liquid, gas, or aqueous? Aqueous, that's right. Okay. Okay, Bailey. Is it balanced? No. What do I need to do to balance it? And am I missing anything else? And a 3. Okay. Okay, is that balanced? Okay, so we have a balanced chemical equation. So now we need to get our total ionic equation. Okay. So what's going to happen? I find the charges. So Mg, it's going to be positive. Are you sure? Are you sure? What was that? Is it going to separate anything? So we're just going to write it as it is. It stays as it is. Okay. We have iron. It is a single replacement reaction. That is correct. Okay, we have iron 3 chloride. So what's going to happen in the iron 3 chloride? That's an aqueous solution. Johnny. You said it's going to be 2 Fe. Is it just going to be 1 plus? Does it? I believe it. What was it? Positive 3 charge. That's right. Iron 3. Okay. Positive 3 charge. AQ. Plus. Remember, it's Velcro. So how many should I have? Are you sure? How many? So Velcro. So now here you have, okay, this is the iron. So iron is kind of like the cloth or the clothy part, yeah. And then each of the chlorines are like sticky part. So the chlorines are sticky. There's 3 of them, right? But we have 2 total, right? 2 total of these. So how many should I have altogether? I should have 6. That's right, Ashley. Alyssa, sorry, Alyssa. Because the coefficient tells us that we have to have 6, right? So there's 2 times. That's right. So we have one iron chloride here. We have another iron 3 chloride. Yes. That's right. Because you have 3 chlorides that were there. They have to stay there. The law of conservation says they have to be there. Now they're just separated. Right? Yes, ma'am. What was that? No, it's law of conservation, you know. It'll stay in solution if it's not being used. Yes. Well, you figure out the coefficient by balancing the chemical equations. That's why it was important for us to balance the chemical equations. The very first step, right? So the way that you balance it, it tells you the reaction. It says magnesium metal reacts with iron 3 chloride. So that's the first thing that we did. We wrote the magnesium metal, we wrote the iron 3 chloride, right? Then we know that this is a single replacement reaction. We know that it's capable of happening. So then we know that we get magnesium chloride and we get iron, right? So then you just balance it out like you would do it normally. Do you understand? Okay, so let me see if I can explain this a different way. Okay, so when I gave you a chemical equation, right? If I gave you just magnesium plus chlorine, iron 3 chloride yields magnesium chloride and iron, how do you balance that out? How did you balance it out before? What was that? No, but you put the coefficients in there because you're putting the coefficients in there. How do you do that? How do you decide which coefficients go in there? What you put in, you must get out, right? Okay, so remember, we have to balance it on both sides of the equation. It has to be what we put in is what we get out. So you did that, right? So if you guys, we would have put the normal way that I would normally do it. I'd put Mg down here. I'd put F. Remember that? All right. So that's balancing the chemical equation. So that's what you have to do to get your coefficients. The very first step is to write out the chemical equation. Write out what's reacting. Make sure that's correct. Why does iron have a 3 positive? Because iron is iron 3. Remember those Roman numerals back in the beginning of nomenclature. Remember, this stuff is additive. You're going to keep adding on to it. Well, we're not done with this one yet. Let's finish this one first, and then we'll do another example. Just relax. Okay, so what are we going to get on the other side of the equation? We have MgClAq. Is that going to separate? Or is it going to stay together? What was that? Okay, so I want you to think about this. AQ means that we're going to do what? Are we going to stay together or are we separating? We're separating. Okay, so then how many magnesiums do I have? 3. And what is that charge on those magnesiums? It's a +2. That's right. Your periodic table. Yep, we know that magnesium is in group 2 metals. Take a look at your periodic table up on there. Group 2, right? Group 2 metals are always going to be what charge? +2. When it forms an ion, it's going to be a +2 charge. Group 1 metals are always going to be what charge? It's always going to be +1. 1 away from being a noble gas. It's always going to be +1. when it forms an ion. Yes. What was that? It isn't a negative. It isn't a negative. Group 1 metals will never be negative. You tell me. Nope, noble gases are negative. Noble gases are always going to be neutral for the most part. When it's a non-metal, so group 17, what's going to be the charge on group 17? Always. When it forms an ion, it's always going to be a -1 charge. Okay, so Cl is going to be what? It's going to have a negative charge. Okay, and I should have, that's right, I should have 6. Okay, now what about this iron? We're going to leave it the same. Okay, so who are our spectators? Yes, you can. And that's it, because this doesn't have a charge on it, this does. That makes them different. Yeah. Okay, so our net ionic equation is just going to be what's left over after we get rid of our spectators. Two Fe. Solid. Okay, are we good? You got this? Okay. Okay. If not, don't worry about it. We have another problem. Okay, let's see. So this at the end of the day is our total ionic, I mean, not our total, our net ionic equation. So we've got rid of the spectators. Total ionic equation has the spectators, net ionic equation gets rid of them. Okay. How are we doing on time? We're out. Okay, so let's do one more, and then we're going to call it a day for today. No, call it a day for lecture. You're not getting out of that easy. Don't get all happy on it. Okay, ironel is dropped into a solution of hydrochloric acid. So in this case, you guys have to tell me what is going to be the product. So what are the reactants? Hydrochloric acid. Okay. And Fe. So I'll give you a hint. Anytime that you have a single replacement going on, almost all of the ions that will be generated, except for the ones that are group 1 metals and the ones that are group 2 metals, are going to be a +2 charge. They're going to be 2. They're going to have a +2 charge. All of them except for silver and aluminum. Okay, so what should be the product? Cl Fe, Fe, Cl, plus, I'm going to tell you this also, this is going to be AQ. Because I know that iron 2 chloride is soluble, meaning it can be dissolved. And I'll show you why in a minute. So, yes. She's making sure that I have things for you. Okay, so what else am I gonna ask? What else? Not yet. H, what? Because we know that H is what? What was it? Not H positive. So when you have H by itself, it's, nope, it's not gonna be positive. It's a gas. Okay, it's gonna be a gas and something else. H2, because we know that it's, what was it? Have no fear of ice cold beer. It's a diatomic. We know that it's a diatomic. Okay, so is this balanced? Haley, is this balanced? Okay, how do I balance it? Okay, so I added 2 to the HCl. And that's good, right? Now we're balanced. Okay. Okay, questions, concerns, Cash? Are we done? Are you sure? Okay, so it's balanced. Is it not balanced? Okay, so I want the net ionic equation for this. Is it, are we done? Okay, so how do I get the net ionic equation? I break them apart. Okay, so 2H plus plus 2Cl negative. Okay. And I'm going to leave that iron alone. I'm just going to drop it down the way it is. Okay. Fe. Is it 2 positive? 2 positive. Are you sure? How many chlorines? Yep. How many Cls? 2 Cl, what's the charge? 2 Cl negative, AQ. Plus, I leave it alone, that's right. Not yet, you're not leaving yet. Okay, our wallflowers are who? Chlorine, okay. Okay, so then what's gonna be left over? Okay, do you guys get it? Are you sure? That's it. Piece of cake. Any questions? Okay. Okay, well, with that, if there aren't any questions, we are stopping here. I will see you guys tomorrow for our very last lecture. Because I'm a geneticist. Because I'm a geneticist. You're saying, why am I not using my degree instead of teaching? I had an opportunity, we'll put it like this. I had the opportunity, let's see. I was in industry for several years. I made a lot of money in industry, spent a lot of money in industry. And I was not happy, right? Wasn't happy doing what I was doing. I actually started teaching. I'm going to be totally honest with you. Totally honest. There's more to it, more to the story. I'll give you a little more detail, but totally honest with you. So I decided to quit my job for two reasons. One, I hated my job, right? Although I love the traveling, some of the people were really good, but ultimately I wasn't doing the things that were making me happy. Was unhappy. If I'm unhappy, I'm not going to stick with it. I'll tell you straight up. You can take this and stick it up your butt, right? Got to catch myself. Don't want to burn bridges, so I always caught myself not doing it. So I decided I was going to go out and start my own company. During the time that I was going to start my own company, the environment was not. I'll tell you. Just wait. Let me tell the story the way I tell the stories. Yeah. No, it's not that mysterious, believe me. Okay, so I decided that I was going to start my own company. And to give you a little more information, it was in biotech, right? Using combination of chemistry and biology, right? And it was in the area of cancer and also infectious diseases. Okay, so now I had this great idea. I thought it was a great idea. I still think it's going to have to change a lot now because there's a lot of little things in the market today than were. I'm not independently wealthy. I come from a poor background. I do a horrible job of saving. I had a little bit of money saved up. Hold on, just relax. Let me tell the story and then we can talk about that another day, right? So hold on. Yeah, but if you let me tell my story, you'll get that. Boy, okay. So I come from a background where my parents lived from paycheck to paycheck. I said I was not going to live from paycheck to paycheck. So I started saving a little bit of money, but I used all my money. My money was going like this, partially for two reasons. One, I was living like I was living when I had a job, right? You can't live that way when you don't have a job. The other thing is that I was trying to use my money towards investment, right? Which meant that I would go out, have dinner with people, talk to them about this, talk to them about that, try to get some prototypes done in the background and all that stuff. It wasn't feasible. So my money was moving very fast. So I had to find a way of making money. So my stepmom, who's a teacher, she actually teaches at the prison. She's like, we have tons of positions. They need tons of instructors at the prison. Here's some information. As soon as they found out that I had a degree in chemical engineering and my PhD in genetics, they were like, oh, we want you. Come teach for us, right? As an adjunct, part-time. So they hired me almost on the spot. I did my interview, pretty much hired me that day as an adjunct. And I'm going to be honest, I'm going to be totally honest with you. I always looked at it because my stepmom is a teacher, my sister were teachers. I always looked at teachers as, they're teachers. They both, don't get me wrong, I love my sister. I love my stepmom to an extent. No, I'm not saying it was easy. I'm never saying it's easy, right? I never thought it was easy, but I didn't realize how much work it was, right? But teaching wasn't something that I wanted to do. It's something that they wanted, right? They like dealing with people and interacting with people and making people happy and make them feel good about themselves. I'm like, I could care less about you, what you do, or anything like that. gonna be totally honest. That's what I honestly thought. I was just like, hey, I want to make money. I do want to change the world. I want to make the world a better place, but I want to make money doing it. Bottom line, I want to make money. That's where I'm at. So I really had no desire to teach, to be honest, totally honest. I got in my very first class. It was at Coalinga, right? They didn't want to put me in the prison. I don't know why they didn't want to put me at the prison, but they decided they were going to have me teach a class in Coalinga, and they were desperate to have somebody teach this class. At West Hills, yeah, very desperate. And my very first class, I had 25 students. I started out with 25 students. First day of class, they had students came in. They were like, Mr. Wanderer was teaching the class. Mr. Wanderer is a bio instructor. It was a bio class. And I'm like, no, I am not Mr. Wanderer. I said, I'm Dr. Henry. They got up, they walked out of the class, right? And so I'm like, okay, so this is a great start, right? Obviously, these students love me to death already, right? And it was funny. That very first semester was the weirdest semester I ever had. Anything that could go wrong went wrong, right? You name it. I was a new instructor. They wouldn't give me a key. You name it, it went wrong. We had one little explosion. It wasn't too bad. Nobody got their head blown off. But a couple things got broken, but it was kind of fun. Wait, hold on. Yes, let me tell my story. I'm telling a story here. Chill, I'm gonna put a piece of tape on her mouth. Okay, so anything that could go wrong went wrong during that semester. But the thing was, the students that I had, and maybe it was just because it was those students, they were incredible. Through thick and thin, the ones that showed up, showed up. And at the end of the semester, there were only 10 students left, but you know, I passed. I didn't expect anything differently. And if you talk to my sister, she'd tell you never take a class. But that's another story. Anyway, I thought it was the best thing. I didn't realize how much fun teaching was. And the other thing, I didn't realize how much fun teaching was at this level. I knew what it was at a school like I did a TA, I was a TA at Case Western Reserve. Case Western Reserve is a private school with a whole lot of money. Anything you can think of, you're gonna have for the lab. Students are coming from all across the world. They're rich, they're wealthy, they're spoiled, right? It's totally different. Here, the class that I had, these students, they wanted to be there, right? They wanted to get that degree. They were busting their asses. I had a student there. She would literally come in from the fields. She had 3 kids. She'd have to go pick up 2 of her kids during my class. She'd still come to that class. She'd make a kid sit in the back, not say one damn word that whole time while they were there. Perfect little saints. You would think that they were mute or something because they would never say anything. They would sit there and work so that she would be able to sit there and take the class, right? So she could try to get her degree. The students that I had there, they gave me 110%. And that changed my life on everything, right? It made me realize that I've had a lot of opportunities. I want to make sure that the students that come through my class, come through my program, have the same opportunities, if not more opportunities than I have. And the opportunities that I have because I've earned them. I've made them happen. Nobody gave them to me. Nobody put it in my lap. I didn't have a mentor. I had mentors that, like, quote, people that say they were my mentors that told me that I wasn't going to amount to anything. I've had things like that rather than people that helped me. I had people that pooped on me, right? And I made it through. I don't want anybody to have to go through what I had to go through to get my degree, right? So I tell you guys the truth. I tell you what's going to be out there. I tell you what it's going to be about, and I make you work your ass off. Because guess what you're going to have to do once you leave here? You're going to have to work your ass off. And especially being a person of color, especially today, you know, you guys are coming from an area that is predominantly Hispanic, right? Right now, the way that America is today, there are a lot of people who are making decisions that are not like us in terms of skin tone. They don't respect us. They don't think we're capable of things, right? And I'm just being honest. I hate to tell it, I hate to break it to you, but the world outside of here is quite different than the way it is here, okay? And you need to be realistic. They're not gonna be your best friends. They're gonna stab you in the back. They're gonna poop on you. They're gonna try to make your life miserable, right? but you have to work through it. You have to recognize what they're doing. You still have to work with those assholes, right? You can't say, I'm not going to work with them. Oh, no, you've got to work with them, but you got to work in spite of them. A lot of times working against things that you would normally not have to work against. And you got to be smart about it. You can't let them make you upset and make you break down. So I have a lot of insight because I have gone through industry. I've gone through academia. What was that? There's fun parts of it, but there's a lot of bad parts of it, you know? The 48 laws of power. Oh yeah, I'm sure it can. Exactly, but that's the thing. But the point is that you've got to be able to pay attention to what's going on around you. You've got to be able to succeed. You've got to be able to, it's good. You guys are great at talking the talk, right? Most of us, we can talk the talk, right? At least fake it to some extent. But in industry, you not only have to be able to talk the talk, you have to be able to walk the walk. When it's time to get the work done, you need to get the work done, right? Do you guys understand what I'm saying? Okay, so the moral of the story was, I love teaching. That's what it turned out to be. It was something that I like. And I'm probably a pretty big asshole to some of you guys, you know? I'll recognize that, I'll own it. But the reason I'm an asshole is because I want you guys to be better than me, right? I want you guys to do better than I do. I want you to make it further than I do, right? Without all of the hangups. So I'm giving you my knowledge.